Hey guys, so we are on to our next chapter or unit, chapter 6, which deals with electrons, how they move around the atom, our electron configurations, our wave calculations, things pretty much that we reviewed from last year with just a couple extra new things in there. So this is called chapter 6, the electronic structure of the atom. Okay, it's good to know that the electrons, right, they don't orbit like planets, they zoom around like bees around a beehive, they're really complex, they follow these probability maps, which if you remember are called orbitals, right? Those orbitals are those probability maps, and there are 4 types of orbitals. And I'm sure you remember they're S, P, D, and F. And remember, these are just kind of like racetracks that the electrons like to chill in. Okay, as we get into bigger and bigger atoms, they get more complicated and complex. So let's talk about that first orbital, which is the s orbital. The s orbital is the simplest racetrack or probability map that you'll see, which is just a sphere. Again, we are focusing on the s orbital. Those electrons are just moving around in a circle-like pattern, 2 bees around the beehive, right? Each orbital can only hold 2 electrons. So again, it can hold 2 electrons, just like any orbital can. There's only one orientation, right? No matter which way you look at a sphere, it always looks the same. So it's just one orientation. Right, and then those sublevel electrons is the collection of the orientations. But since there's only one orientation with 2 electrons, there are only 2 sublevel electrons. Okay? So that's the s orbital. Let's go ahead and let's focus on that p orbital. Remember, the p orbital has a dumbbell shape. Okay, dumbbell shape. It can only hold 2 electrons as well. Any orbital can only hold 2 electrons. But the difference with s and p is that p orbitals have 3 orientations, right? They have a flat one, like so, and they have a diagonal one, like that. And each orbital can hold 2 electrons, okay? But sublevel electrons, right, is the collection of all those orientations. So if I stacked all those orientations onto one another, then our sublevel electrons would be 6. And you see this with our electron configurations, right? 1s2, 2s2, 2p, 6. So now let's talk about d orbitals, okay? We are now on to d orbitals, and they look like a dumbbell. Okay, so if you were to think of this in 3D, it'd be 4 balloons stacked on top of each other, and just like every orbital, they can only hold 2 electrons. Okay, so they can only hold 2 electrons. They also have 5 orientations. Okay, so they have. I'll attempt to draw all these, not to scale. There's one where you look at it sideways, and then there's one that looks like a donut, right? So there are 5 orientations for the d orbital. Again, these are racetracks that they like to zoom around. And again, each of those orbitals only holds 2 electrons, so that would give us a total sublevel electron of 10. Sublevel electrons. Now, let's go to the last one, which is F, which looks like a flower. It's like if you had 8 balloons attached at the stem to one another. Okay, I'm not going to draw all the orientations, but you could guess that S had 1, P had 3, D had 5, F is going to have 7 orientations. each of those orientations could only hold 2 electrons. So after I stack all those orientations onto one another, you're going to have 14 sublevel electrons. Okay, so 14 sublevel electrons. Things from last year that we also have to talk about. So know those orbitals, okay? Know their shapes. Know that they can only hold 2 each. But from last year, what we got to talk about some more is some of the nomenclature and the terms that go along with electrons. So let's talk about energy levels, right? You might remember absorption and emission, okay? They will dictate the energy levels as the letter N. Okay, so this is the nucleus right here. The first energy level they will just say is N equals 1. Second one is N equals 2. Third is N equals 3, N equals 4, and so on up to 7. Right? We have electrons jumping from levels and dropping to certain levels, right? Say it's at N equals 2 and it goes to N equals 3. What happens there is that electron will get excited. It could be electricity, it could be fire, okay, it could be heat. It'll excite that electron and it will jump to the next level. Remember, that is called absorption. It absorbs that energy. And the cool thing is that when it jumps from the second level to the third level, there's no trace of it whatsoever in between. So it's kind of like it teleports almost. Scientists are still kind of trying to figure that out. So it'll go from 2 to 3. So if I say 1 to 4, or 2 to 3, or 2 to 4, or 2 to 5, that's absorption. That's when it jumps a level. But then there are the times when it'll go ahead and it'll drop a level. And when it drops a level, it won't absorb energy. It'll release it. Okay? It'll release the energy. It'll emit it. That's called emission. Okay, we saw this last year when we were burning different colored salts, right? Depending on where they drop from, they release different wavelengths, which releases different types of colors. So absorption and emission from these N equals 1, 2, 3, 4, all the way up to 7 monikers. Now remember, when that light comes out of those electrons from emission, they come off in waves. Particle wave duality, but we'll think of light mainly as waves, where the wavelength is from crest to crest or trough to trough. Okay, so let's look at kind of a wavelength, kind of a path like this. Okay, there's 2 things we look at: wavelength and frequency. Okay, this side has a long wavelength. If you have a long wavelength, you're not going to be getting hit with as many waves. You're not going to be getting hit as frequently. So this is also a low frequency. So low wavelength, long wavelength, low frequency, that also means low energy. If you're not getting hit with a bunch of waves, you're not getting a lot of energy. So this is also a low energy. But then as we get shorter and shorter wavelengths into those gamma rays, okay, we start getting into higher frequency and higher energy. Again, shorter wavelengths here. If I'm getting shorter wavelengths, that means that I'm getting hit with waves more often, okay, more frequent. So I'll have a high frequency. And if I have a high frequency, I'm getting hit with more of those waves. That means that I'm getting more energy. So I'll also have a high energy. Alright, so that's kind of the synopsis of waves. Now let's go into how we calculate wavelength, frequency, energy, and so on and so forth. But before I get to the calculations, I forgot I got to talk about that electromagnetic spectrum, which is the spectrum of all light. So let's talk about the electromagnetic spectrum. It's kind of like what we were talking about earlier. It's just giving names to these types of waves, right? So long wavelength, short wavelength, First thing is in the middle, there's a tiny little sliver of light or wave types, which is our visible. All this is all the type of light you will see, but not really see, but like experience in nature. But the only type that you can see is this tiny little section here of red, orange, yellow, green, blue, indigo, and violet. Okay, so there's tons of light going on. You just can't see it. Okay, our cones can't pick it up. Bees can pick up infrared. I'm pretty sure there are some snakes that can pick up infrared as well, and some other types of light, but we can't see it. If you could see all of the light, you'd be seeing all this crazy UV light, a bunch of radio waves as well you'd be able to see. Gamma, you're not going to see too much because the atmosphere blocks that out. But anyway, let's talk about the spectrum. Over on these left sides, you have radio waves. Okay, they're really long. They could travel far distances. They don't have a lot of energy, right? That's why they don't cook us when we're listening to the radio in the car. Next up is microwaves, which you might think is weird because aren't microwaves dangerous? They're really just dangerous to water molecules, okay? They excite water molecules a lot. They're not really dangerous to much else, okay? They just they're like the perfect wavelength to excite a water molecule. Okay, so when you're cooking stuff in the microwave, it's just the water that's getting heat up, right? And then you might be saying, well, why is my plate hot? It's just that your food is transferring heat to the plate and making it hot. Microwaves actually won't heat up a plate or a bowl or anything like that. Next up is infrared. Okay, which is just like heat light given off. Then we got our visible area right here. Next up we got ultraviolet, which are your sun rays. Okay, they're just long enough to get through our atmosphere, but they're not short enough to cause too much damage, right? If we're in front of ultraviolet for too long, it will denature our skin and burn us a little bit. Next up is X-ray, right? Hopefully you've never had to get an X-ray. I've had to get a couple, right? But those are some dangerous wavelengths. That's why they put that lead sheet over you so you don't get any damage from those. And the last one is gamma, which pumps you full of a bunch of energy and could possibly mutate your cells. A lot of astronauts get it when they go up into the space station, but we're safe here. Okay, those wavelengths are too short. They can't get through our atmosphere. Okay, it's the long ones that are able to sneak through, but those short ones, they get blocked by the smallest thing, including just our atmosphere of nitrogen. So that's the electromagnetic spectrum. Alright, next up we just got to talk about those light equations. Again, this is stuff from last year that we talked about. And there were two equations that we're going to focus on. Okay, that got some weird Greek symbols in there. The first one is C equals lambda V. Okay, C being a constant, which is the speed of light. Okay, speed of light is how fast light travels. Duh. Okay, it's 3 times 10 to the 8th meters per second. Nothing can go faster than that. Okay, if you start to approach the speed of light, time starts to slow down for us. We'll talk about that some other time. Lambda, Greek sign for lambda, looks like the giraffe, right, is wavelength, which is measured in meters. And then V, or nu, it's really the Greek letter nu, but I'm going to say V, okay, because that's what it looks like for simplicity's sake, is the frequency. So how often the waves are hitting you. And those are in hertz, okay, which is the same thing as 1 over second, right? Things over seconds. Waves per second. If you're in a hot dog eating contest, hot dogs per second, your frequency of eating hot dogs. Okay, kicks per second if you're beating up somebody. All right, so that is our first equation. Okay, next equation is E equals hv. So this is relating energy to frequency. Okay, frequency is still the same, so I'm going to leave that. E is energy, which we measure in joules. Okay, joules isn't a really, for every 1 calorie of food, you have 4,184 joules. So it's a tiny, tiny unit. Joules, J-O-U-L-E-S, not J-U-U-L, not that stuff that gets you addicted to nicotine, right? H is Planck's constant. I'm not going to write it. It's Planck's constant. Okay, it's named after a scientist. And that is 6.626 times 10 to the negative 34th joule seconds. Okay, so it's just a constant, 6.626, right, like Stitch, to the negative 34th. And they will give you that, and that should be on your AP equation sheet. So next we'll do some examples. But before we do some examples, we got to talk about nanometers. Okay, that's how they're going to give you a lot of these wavelengths. They'll give them to you in nanometers, especially when we're dealing with visible light. Okay, the only thing you need to know is that there are 1 times 10 to the 9th nanometers in 1 meter. Okay, you got to know that conversion. They won't give it to you, but if we're working with nanometers a lot, you won't have to worry about stuff like that. Okay, so I'll explain. We have 500 nanometers, right? And we want to convert that to meters. So we just do a little dimensional analysis here, right? For every 1 meter, there's 1 times 10 to the 9th nanometers. We go ahead, we solve that in our calculator, and it should give us 5 times 10 to the negative 7 meters. Okay? We might get something else like 430 nanometers. Well, we got to change that to meters if we're going to plug it into any of our equations. Once again, we do the same dealio. We just divide by 1 times 10 to the 9th. And you should get 4.3 times 10 to the negative 7th meters. So you can kind of see a pattern here, right? This was 5 times 10 to the negative 7th. This is 4.3 times 10 to the negative 7th. You can start to just see that, okay, it's always going to be times 10 to the negative 7th. So if I gave you like 700 nanometers, right, you could just say, hey, that's 7 times 10 to the negative 7th meters. If I gave you 850 nanometers, you could say that's 8.5 times 10 to the negative 7th. If I gave you 300 nanometers, you could say that's 3 times 10 to the negative 7th, okay? So you're going to be doing a lot of converting, okay, and be able to go vice versa, right? You can know this is 500, just add 2 zeros, 2 zeros, 2 zeros, okay? So 700 nanometers, 430 nanometers, 500 nanometers. Okay, so we're into our light calculations now. We're only going to do 3 examples and I'm done. So here it says determine the frequency of light whose wavelength is 425 nanometers. Well, I know I only got 2 equations that are going to help me figure that out, and that is E equals hv and C equals lambda v. Right, those are my 2 equations. It's wanting frequency, so it could be either of these for right now, right? Wants frequency, but then it says whose wavelength is 425 nanometers. Well, the only thing that deals with wavelength and frequency is that bottom one, C equals lambda v. So let's go ahead, let's start plugging and chugging, but let's make sure we get that nanometers into meters first, right? We can't plug it in. Our units wouldn't match if we plugged it in with nanometers. So 425 nanometers, you might be able to do this in your head without me doing the dimensional analysis. But if not, we remember 1 meter is 1 times 10 to the 9th nanometers, giving us meters of 4.25 times 10 to the negative 7. Okay, here we go. Plug and chug time. C is a constant, 3 times 10 to the 8th. They will give you that on the formula sheet. Okay, lambda stands for wavelength, which we just found in meters, which is 4.25 times 10 to the negative 7 meters. And then we want frequency. Pretty simple from here on out. We just do a little algebra, make sure that we're putting in our calculator right so we don't get any order of operation errors. To get to nu by itself, we just divide by 4.25 times 10 to the negative 7th. Meters cancel out, which is good, leaving us with just 1 over seconds, which is the units for frequency. So we should get something like 7.06 times 10 to the 14th hertz, or 1 over seconds. It doesn't matter. Either unit is good for me. It's good enough for the AP College Board. So let's go ahead and go to the next example, okay? I don't want to determine the frequency anymore. I want to determine the energy of a photon with frequency 3.55 times 10 to the 17th hertz. So here I give you energy, or I want energy, and I give you frequency. Right? We're going to be using this guy. We got frequency, we want energy, we know Planck's constant. Plug and chug time, guys. Energy is what I'm looking for. H is 6.626 times 10 to the negative 34th joule seconds. Frequency is 3.55 times 10 to the 17th hertz, which is 1 over seconds. Okay? Seconds on top, seconds on bottom, they cancel out, left with joules. We know we're on the right track. We multiply those together, and you should get something like 2.35 times 10 to the negative 16th joules. Alrighty. Last one, guys. Last one. And you know what's coming, right? We're going to have to use both equations. Both equations. So, we're going to do, let's say, what is the energy of light with a wavelength of 600 nanometers. Okay, they want energy. They give us wavelength. This is the equation for energy, but unfortunately, there's no wavelength in here. But luckily, I have another equation that helps me take wavelength and change it to frequency. Okay, so what I'm going to do is I'm going to use this equation first, then I'm going to solve for frequency and plug it into this guy and solve for energy. Okay, so let's go ahead and do that. First things first though, I gotta get that nanometers into meters. We should know that it should be 6 times 10 to the negative 7th meters, right? So let's get going to figure out frequency that this light gives off. C is 3 times 10 to the 8th meters per second. Wavelength I just figured out, which was 6 times 10 to the negative 7th. And I gotta solve for frequency. Do a little algebra here. Should leave us with a nice frequency of 5 times 10 to the negative 14th hertz. To the 14th hertz, not negative 14th. 14th hertz, okay? Then, now that we got frequency, we can plug this guy into our E equals HV equation. E equals Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. Frequency I just solved for, which was 5 times 10 to the 14th hertz. We multiply those together, we should get something like 3.3 times 10 to the negative 19th joules. Okay guys, that is our light calculations. That's as difficult as they get. Have yourselves a great day.